For our first Try Me problem, consider problem 492 involving a Chinook helicopter. Given the information in the problem statement, we are to find the equivalent force system at O, which also appears to be the helicopter's center of gravity. Take some time to try the problem yourself. Resume playing when you are ready to see a solution. This is a nice problem for several reasons. It shows how a complicated machine with several different sources of propulsion can be used to make the vehicle stationary. In hover mode, for instance, the net force and the net moment about the center of gravity should be zero, or to propel the vehicle in different directions and attitudes depending on the components of net force and net moment. Before we get to the details, I want to focus on one part of the problem statement, that being the sentence, "The rotors counter-rotate so that a vertical stabilizing rotor is not needed." What exactly is meant by this statement? Let's consider first a traditional helicopter, one you would see covering traffic reports or perhaps transporting accident victims to the hospital. Such a helicopter has one main rotor and then a much smaller tail rotor that is in fact the vertical stabilizer. Why is the stabilizer necessary? The helicopter's main engine exerts a torque on the rotor to bring it up to its steady angular velocity, as represented by the red arrows in this figure. But there is an equal and opposite torque in green on the body of the helicopter. Without another source of torque to counter this, the helicopter's fuselage would spin around the rotor axis in the opposite direction of the rotor so that the net angular momentum of the system, the helicopter plus rotor, is zero. I realize the term angular momentum is unfamiliar. It's the product of rotational inertia and rotational speed. The helicopter's fuselage has a much larger rotational inertia than the rotor blades, and what this means is that the helicopter fuselage doesn't need to spin nearly as fast in the opposite direction as the rotor blade to conserve angular momentum. Still, even a modest rotational speed of the fuselage would be disastrous. Although you've never seen it live, there are plenty of Hollywood action movies depicting accidents resulting in the loss of the vertical stabilizer, where the helicopter spins out of control and crashes. The purpose of the tail rotor is to provide a force normal to the helicopter's symmetry plane, as indicated by the yellow arrow, that exerts a counteracting torque to keep the helicopter stable about its rotor axis. The Chinook helicopter's design employs two large, counter-rotating rotors whose moments on the Chinook's fuselage nearly cancel out. You will notice from the problem statement that these two moments are large, but not quite equal and opposite. In both the traditional and Chinook helicopter main rotors, the assembly driving the main rotor involves a complicated piece of machinery called a swash plate that permits the rotor to be tilted side to side and fore and aft so that the direction of the force provided is not purely vertical. In the present figure, rotor lift is designated by forces QA and QB, but you will also notice much smaller forces FA and FB at shallow angles off the y-axis. These can be thought of as resulting from pilot adjustments to the swash plates so that the rotors are not purely in planes parallel to the XY plane. These forces also contribute to vertical torque and help balance the net moment about the z-axis. Finally, in addition to the rotors, there are small engines mounted symmetrically along the helicopter's fuselage that help propel it forward. These are seen in the forces at C and D along the y-axis. Our interest is in finding the equivalent force system at O, which, as I mentioned, I'll assume this is also the center of gravity G. But then how should we interpret those results when we get them? If the helicopter is in hover mode, we'd like the net forces and net moments to cancel out. We might note that the helicopter's weight is not provided, so hover mode in this case probably means the net lift force in the z direction is assumed to just balance the weight of the helicopter. Non-zero net forces in the x and y directions would provide thrust forward and to the side to propel the helicopter in different directions. A net moment about g in the x direction would influence the pitch of the helicopter, that is, whether its nose points up or down, and a net moment in the y direction would influence the roll, whether it banks to port or starboard while making a turn. Net moments in the z direction are generally to be avoided in aircraft, as this corresponds to the dreaded yaw rotation, the most stomach-churning of all maneuvers. Helicopter pilots may adjust their controls to provide a temporary non-zero yaw moment in order to pivot the aircraft around quickly and head off in a different direction, but it is only a temporary net load. With all that as background, let's now attend to the business of finding the equivalent force system at O. First, we have a resultant force, which we can write as force magnitude A on the unit vector that points in the direction of A, and since the problem statement tells us that FA and FB lie parallel to the XY plane, we know that the unit vector that describes the orientation of FA can be written in this case as sine alpha A in the I direction plus cosine alpha A in J. Similarly, for the force at B, we have the unit vector being sine alpha B in I plus cosine alpha B in J. And then we have the forces at C and D, which are simply, they're both in the y direction, so FCJ plus FDJ. And then we have the lift forces QA and QB, both in the K direction. For the resultant moment, we have first, given the directions in the figure, we could write these as MB in the K direction minus MA in the K direction. Then we have two sets of forces acting at both A and B, and so we can write plus RA crossed into QA plus FA plus RB crossed into QB plus FB plus RC cross FC plus RD cross FD. So symbolically, that's the result of our calculation. Now we just have to plug in all the numbers and get the numerical values. For the resultant force, we have 700 pounds on sine 5 degrees in I plus cosine 5 degrees in J plus 600 pounds on sine 8 degrees in I plus cosine 8 degrees in J plus 400 pounds in J from both C and D plus 9,000 pounds in K, and then another 8,000 pounds in K. The net result of all that is 144.5 I plus 2091 J plus 17,000 K pounds. And in terms of interpreting that, let's assume that the helicopter weighs 17,000 pounds so that the z direction component zeroes out. And so this result tells us we mostly have a net force at this instant that is propelling the helicopter forward along its plane of symmetry, along the y-axis, with just a little bit of lateral force side to side in x. Now we'll consider each of the moment terms. For the first cross product term in the resultant moment, we have this RA cross QA plus FA. RA has components 0, 35, and 12 feet, and the sum of QA and FA have the components shown here: 700 sine 5 degrees in I, 700 cosine 5 degrees in J, and 9,000 pounds in K. We can evaluate that cross product and get these results. And if we evaluate all that, we end up with these numbers for the moment about O from the forces at A. We can now evaluate a similar term from the forces at B. That cross product looks like this. And evaluating those terms, we have these results. And the numbers that follow from this have these values. Finally, we have the contributions from C and D, and these are a little easier to evaluate since the force provided by those engines is just directed along a single coordinate direction, in this case J. So we have RC cross FC is 9I minus 40J plus 8K feet crossed into 400J pounds. And that gives us, from the first term, we have 3,600 on I cross J. And then the last term, we have 3,200 on K cross J. And using the fact that I cross J is equal to K cross J is equal to minus I, we have that this is minus 3,200I plus 3,600K foot-pounds. The contribution from the other engine is nearly the same value. There's just a change in one sign. Our position vector now is minus 9I minus 40J plus 8K feet. And what we can see from that is that's just going to change the sign of the second term. This is going to end up being minus 3,200I minus 3,600K foot-pounds. So to get our resultant moment, we just add all these different contributions together, and the individual numbers end up looking like this. Now, if we take a look at that final result, we have a relatively large moment about the negative x-axis, which tells us that this is going to tend to pitch the Chinook forward so its nose points towards the ground. There's a little bit of a net moment in the J direction, which would tell us that this would tend to bank just a little bit to its starboard side, to its right. And finally, that we have just a little bit of yaw moment in the minus Z direction. We might just note that if we wanted to zero out that yaw moment altogether, this could be achieved with a very modest change to the rear swash plate. Instead of having an 8-degree angle of inclination for the force FB, we could change that to a 10-degree angle, and the result of that would be to nearly zero out that yaw moment altogether. Still, it is exactly this kind of calculation from all these different sources about the center of gravity that tells us what the motion, what the translation, and the rotation of the vehicle is likely to experience as a result of all of these things acting in concert.